Cabinet 1. On the top shelf is a Wimshurst machine developed around 1882 by the British inventor James Wimshurst. It is the most powerful machine invented in the 19th century for the generation of static electricity. It consists of two contra-rotating glass or ebonite discs, each carrying narrow strips of tinfoil. At each side are collecting combs attached to Leyden jars, which are not seen here, and discharging electrodes. Today, such an apparatus is normally replaced by a Van de Graaff machine. At the right of the top shelf is an electrostatic chime. In this apparatus, an electrostatic charge produced by a Wimshurst machine was placed on the large inner hemisphere. The metal chime balls were attracted to the hemisphere where they picked up a charge and then were repelled to strike a chime bell. The order of the striking the chime bells was set by adjusting the distance between the bells and the chime balls. In the center of the shelf is an assembly of two brass hemispheres and a brass sphere. Such a setup was used to show that electrostatic charge will move to the surface of the sphere, leaving no charge in the interior. In this cabinet are many models of galvanometers and electrometers, sensitive instruments to measure small quantity of current and charge. A galvanometer is an electromechanical instrument used for detecting and indicating electric current. A galvanometer works as an actuator by producing a rotary deflection of a pointer in response to electric current flowing through a coil in a constant magnetic field. On the bottom shelf are examples of resistance boxes. They were used for precision electrical measurements. Precision measurements were one of the professional hallmarks of a good teaching practice. In a simple resistance box, the resistance can be varied by removing some of the copper studs. In a decade resistor box, like that at the back, the resistance can be varied by the rotary switches. Cabinet 2. The top shelf shows diversified apparatus. On the left in the back is a Cornell Dubilier capacitance analyzer. In front is a demonstration of a parallel plate capacitor. Two glass jars on wooden bases run along a wooden track with a scale. There is a cork in the top of each jar through which a glass rod runs. Connected to the rod is a round brass plate, so that the two plates are vertical and parallel to each other. In the back on the right is a Coulomb torsion balance. Such apparatus was used by Coulomb around 1780 to measure electrostatic forces. In front are examples of mica condensers. The center shelf presents a collection of meters used for various measurements. Most of them are voltmeters or ammeters. At the left in front is a standard voltmeter used in Great Britain in the 1940s. At the back left is a Wheatstone bridge used in England by the post office to evaluate the properties of their telegraphs. Cabinet 3. At the right of the top shelf is a working model of a Wilson's cloud chamber invented in 1911. It is a particle detector used for visualizing the passage of ionizing radiation. A cloud chamber consists of a sealed environment containing a supersaturated vapor of water or alcohol. An energetic charged particle interacts with the gaseous mixture by knocking electrons off gas molecules via electrostatic forces during collisions, resulting in a trail of ionized gas particles. At the left are models of engines. Most late 19th century treatments of heat and thermodynamics made little distinction between physics and engineering. Various engines were used for demonstration purposes. One such item is a demonstration model of the internal combustion engine produced by L.E. Knott Apparatus Company in Boston near 1910. At the back of the middle shelf are in order a Leeds and Northrop Wheatstone bridge test set, two galvanometers, a gyroscope, and a flux meter to measure magnetic field. In the center of the bottom shelf is a large high-frequency transmitting triode. The tube requires forced water cooling. It can be used as an amplifier or oscillator up to 20 MHz. It was used in the RF amplifier of the McGill cyclotron. Cabinet 4. In Cabinet 4, the top shelf presents apparatus related to the effect of magnetic field. On the left side is what is called a Faraday's disc. In this apparatus, a large copper plate is charged and then rotated. This generates a magnetic field which provokes the needle to resolve. On the right is an example of a Helmholtz coil. A Helmholtz coil is a device for producing a region of nearly uniform magnetic field, named after the German physicist Hermann von Helmholtz. It consists of two electromagnets on the same axis. Besides creating magnetic fields, Helmholtz coils are also used in scientific apparatus to cancel external magnetic fields, such as the Earth's magnetic field. With the aid of the compass in the center and a variable power supply, the terrestrial magnetic field at any point could be determined. On the bottom shelf are also interesting apparatus. On the left is a table model electron microscope. This RCA permanent magnet electron microscope is a simplified low-cost instrument designed to bring the many advantages of electron microscopy within reach of more laboratories and schools. The use of permanent magnet lenses in this model makes it possible to eliminate many of the controls and much of the bulk of the larger research model. The built-in camera has a direct magnification up to 6,000 times, and it could resolve two objects separated by 100 angstroms or 10 to the negative 8 meters. At the right are two large early X-ray tubes. It consists of a concave cathode where electrons are produced and accelerated towards the target. The concave shape and the ring in front of the target help focus the electrons on the target where X-rays are produced. At the back is a neon tube used as a sign for the McDonald's physics building. Cabinet 5. On the right of the top shelf are examples of slide rules. The slide rule is a mechanical analog computer. It is used primarily for multiplication and division and to calculate functions such as exponents, roots, logarithm, and trigonometry. The large cylindrical slide rule is a Thatcher's calculating instrument. It was patented by Edwin Thatcher in 1881. With this folded scale, though it fit on a desk, it was equivalent to a conventional slide rule over 59 feet long. The small wooden rule in front is a boxwood slide rule created around 1860. It is sometimes called an alcohol rule, used for calculating the quantity of liquid in a cask and or the excise duty payable. The center shelf presents a bust of Howard Barnes, who was the second chair of the physics department from 1909 to 1919, equally well known for his work in basic science and in practical applications. His most important national contribution was perhaps his quantitative analysis on how the residual winter heat content of Lake Ontario could be made to give an ice-free channel to the salt water near Quebec City. He also collaborated with Ernest Rutherford measuring the energy produced in radioactive decay. He was a leader on ice research and wrote two books in the field, Ice Formation in 1906 and Ice Engineering in 1928. On this shelf is also a small collection of high-precision mercury thermometers used for temperature measurements. Two are particularly interesting. The front thermometer on the left has a small range from 0 to 6 degrees Celsius over 18 centimeters, so that each line corresponds to 0.01 degrees Celsius. The front thermometer on the right has a double range from negative 0.5 to 1 degree Celsius and then continues from 15 degrees Celsius to 33 degrees Celsius. At the back of this shelf is an electrical pyrometer. In the total radiation pyrometer, radiation emitted by the source is focused by a concave mirror onto a blackened foil to which a thermopile is attached. From the electromotive force produced by the thermopile, the temperature of the source can be calculated. Hugh Callender, a professor in the department who worked with Howard Barnes on the electrical equivalent of heat, developed and patented this instrument. It was rescued by Professor Stevens Newsham from the McDonald Physics Building and sent to McGill in 1987. Cabinet 6. Most physics texts at the turn of the century contain some physical explanation of the physiology of hearing, vision, and speech. The plaster model of an ear at the right of the top shelf was probably purchased from the Scientific Supply House of E. Labeled in Cologne, Germany. The shelf contains many tuning forks. At the left is a box containing many precision tuning forks made by Rodolphe Koenig, a master instrument maker based in Paris. They were used sometime in conjunction with other instruments to study sound. In the center is a large Helmholtz resonator. In the display at the entrance to the building is a collection of such resonators. A Helmholtz resonator is a cavity where air oscillates at a particular standing frequency. It was widely used in the study of acoustics. On the middle shelf is a collection of discharge vacuum tubes from early 1900s. They include Geisler and Crookes tubes. Some were used as a source of X-rays, while others were used for demonstrating the presence and properties of electrons. At the left, the display contains 4 X-ray tubes used in medical X-ray apparatus. At the back of the bottom shelf is a Geisler tube. It is an early gas discharge tube used to demonstrate the principles of an electrical glow discharge, like modern neon lighting. The tube was invented by the German physicist and glassblower Henri Geisler in 1857. Our model has colored decorative serpentine paths formed into the glass tube. In the front is a vacuum tube with a fluorescent screen. This tube includes various electrodes that allow orientation and focusing of the electron beam on the fluorescent screen. Cabinet 7. At both extremities of the top shelf are examples of a Nuremberg polariscope or doubler. These were used for examining crystals, quartz, mica, optical glass, etc. in polarized light. In this instrument, the light is polarized using a tiltable glass plate. The design is attributed to Johann Gottlieb Christian Nuremberg in the 19th century. The middle shelf contains a small collection of diffraction gratings. In optics, a diffraction grating is an optical component with a periodic structure that splits and diffracts light into several beams traveling in different directions. Diffraction grating replaced prisms that were commonly used beginning in the 19th century in monochromators and spectrometers. At the left are 3 small gratings produced between 1892 and 1923. They have a pitch of roughly 30,000 lines per inch and were ruled on Henry Rowland's engine that one sees in the photo. Nowadays, plain gratings are often ruled onto a thin layer of aluminum deposited on plain glass. The diamond ruling stylus is thus subject to little wear. This is the basis of the large grating presented in the center of the shelf. The large apparatus at the left of the bottom shelf is a Becquerel phosphorescope. This gear chain was used to rotate 2 discs mounted on the top frame. A phosphorescent crystal was placed between the discs, and the lifetime of the phosphorescence could be determined by estimating the time delay between the slits on the disc. Since the lifetime of the phosphorescence could vary from a fraction of a second to several hours, the range of speed of the gear chain needed is seen below. At the right is a Regna chronograph built by Rudolf Koenig. It was used to measure the sound velocity. Cabinet 8. On the left of the top shelf is a small collection of various optical prisms used in the study of light. At the left of this collection is an example of Newton's rings. It is a phenomenon in which an interference pattern is created by the reflection of light between 2 surfaces, a spherical surface and an adjacent touching flat surface. It is named for Isaac Newton, who first studied the effect and is described in Newton's book in the following cabinet. The large brass apparatus at the right is a refractometer. It is used to measure the index of refraction of liquid. It was produced by Dubosc in Paris around 1850. In the middle shelf is examples of various lenses. In particular, one sees a spherical lens that demonstrates that the image on the ocular retina is inverted. Cabinet 9. On the left of the top shelf is a copy of the original edition of Optics by Isaac Newton titled Optics, or a treatise on the reflections, refractions, inflections, and colors of light. It was published in 1704 and was presented to Professor Howard Barnes by Messrs. A. Johnson in 1913. It is considered one of the great works of science and history. Note that Newton's name did not appear on the title page of this first edition. It was added by one of the previous owners of the book. The first edition contains an appendix in Latin where Newton presents some of his important results on calculus. On the top shelf is also a small collection of prisms, the large ones finished by the famous John A. Brashear. The original 6 prisms were used by Foster in his spectrometer to study the Stark effect. With these, it was possible to produce a separation of 1 millimeter per angstrom in the violet. At the right, one sees a small quartz spectrograph manufactured by Adam Hilger. It used a prism made of quartz to disperse the light, and the resulting spectrum is recorded on a photographic plate at the back wall. At the left of the middle shelf is a heliostat. A heliostat is a device that includes a mirror which turns so as to keep reflecting sunlight towards a predetermined target. Our instrument is of a clockwork revolving type with one mirror partially blackened, all in a tripod stand with leveling screws and bubble levels. It was made in England. The center shelf presents also an artificial horizon. In this apparatus, the iron tray was filled with mercury and the glass tent protected the mercury surface from wind disturbance. This instrument was made by the Montreal instrument workers Hearn and Harrison. At the right are 5 wooden frame slides. They were used with the lantern and have handles to revolve the image. The slide shows were used to demonstrate some physics phenomenon. Our slides include demonstration of central disturbance propagating a wave motion, eclipse of the sun, decomposition of white light in colors, and moving pictures. Center aisle. The center aisle contains a variety of interesting items. At the end is the desk used by Rutherford at McGill. It is a roll-top desk. When they cleaned up the building, they found that the top of Rutherford's desk was radioactive. They cut part of the top but kept the desk. On both sides of the desk are old clocks built circa 1860. The right clock had a contact 5 minutes before the hour to mark the end of class. One of these clocks was part of the McGill Observatory first established by Dr. Charles Smallwood in 1863, who moved his homemade observatory from his house north of Montreal to McGill. These clocks not only rang McGill bells, but also kept time for all Canada through the Dominion Observatory time signal. At the end of the center table near Rutherford's desk is a Marconi wireless detector, often called a Maggie. The magnetic detector was an early form of radio detector used during the early 1900s. This magnetic detector was found to be more reliable than the coherer, an earlier form of detector for wireless signals. Such a detector was invented by Marconi in 1902. The present apparatus dates from 1905. It was used in boats, and a similar apparatus was present in the radio office of the Titanic. The McPherson Museum now collects more recent apparatus. At the center of the table is a large Paul trap used by Professor Moore and his colleagues around 1990 for the first measurement of the mass of unstable nuclei using ion traps. The measurements were done at the ISOLD accelerator at CERN. Today, many accelerator facilities in the world have such traps for that purpose. At the end of the table is an old tin-foil phonograph invented by Edison. In 1879, Edison gave a contract to the company Bergman and Company to build 200 of these phonographs. The phonograph used large flywheels to keep the velocity constant. Recording was done on a sheet of tin that was rolled on the large brass cylinder. Tin, being a very soft material, meant the recording could only be played 2 or 3 times. You can see all these items in our collection by looking at the database on the museum webpage that is accessible through the McGill Department of Physics. We would like to thank you for having taken the time to visit our museum.